Welcome to The Explainer. Today, we're diving into a hidden bottleneck, something that's really holding back the full power of AI, and we'll look at the incredible technology that's finally here to smash right through that wall.
Okay, let's start with a number that is, well, it's pretty mind-boggling. Over just the last 2 decades, the raw computing muscle of a top-of-the-line chip, it has skyrocketed by 187,000 times. I mean, that's just an almost unimaginable jump in processing power.
So, the big question is, with all that horsepower, why can't we actually use it all? Well, it turns out all that incredible power is slamming right into a wall, a bottleneck. It's stopping us from getting data in and out fast enough to keep these silicon brains fed. So yeah, let's get into it.
Okay, so here's what we're going to cover. We'll start with AI's hidden power problem and this bandwidth wall everyone's talking about. Then we'll look at a solution that's been waiting in the wings for like a decade and figure out what finally pushed it onto center stage. Hint, it's AI. We'll see how that kicked off a huge race among the tech giants, and then we'll wrap up by looking at what this whole mashup of light and electrons means for what's coming next.
You know, we always focus on how fast a chip can think, right? But the real problem, and this is kind of surprising, is the cost of talking. Seriously, just moving data from point A to point B is starting to use up a ridiculous amount of power.
And that brings us to the bad guy in this whole story, the bandwidth wall. So what is it? Well, it's this huge, growing gap, this chasm really, between how fast our chips can process information and how fast they can actually communicate that information. It's just not sustainable.
So to really get this, let's take a quick look inside a data center. Deep inside, you've got this thing called a switch chip. The best analogy? Think of it like a giant, super busy airport terminal for data. Its whole job is to direct thousands and thousands of data passengers zipping around at crazy high speeds.
Okay, so if the switch chip is the main terminal building, then you need a way to get the passengers in and out, right? That's where the optical I/O comes in. That's the input/output. These are basically the airport gates, the runways, the highways, all the infrastructure that connects the terminal to the outside world. They take the electrical signals from the chip, convert them into light, and shoot them down fiber optic cables.
And right here, this is where you can see the whole problem in a nutshell. The switch chips, the terminals, are made of silicon. They follow Moore's law, so they get twice as fast about every 2 years. It's incredible. But the optics, those gates and roads, they get better but way slower. So what happens? You get a massive gridlock traffic jam. The terminal is getting bigger and more efficient, but the roads leading to it can't keep up.
So there's a specific component whose job it is to bridge this gap between electricity and light. It's called the SerDes. And because the silicon is getting so much faster, the SerDes is having to work like crazy just to keep up. And look at this. It's now eating up more than 30% of the chip's entire power budget. Think about that. Almost a third of the power isn't going to computing. It's just being burned to move data around. That's a huge waste. All right, so we've got a villain, the bandwidth wall. But, like in any good story, there's a hero. And this hero has actually been waiting in the wings for more than a decade for its big moment. It's an idea that, for a long time, just seemed too hard to pull off. And that hero is called co-packaged optics, or CPO for short. The idea behind it is actually super simple, but from an engineering perspective, it's radical. It's basically, hey, if the long distance between the electrical chip and the optical parts is the problem, why don't we just get rid of the distance? Let's stick them right next to each other, in the exact same package. So if it's such a great idea, why did it take so long? Well, CPO had 3 big enemies standing in its way. First, there's heat. Silicon chips get really hot, and that heat completely messes with the delicate, precise light signals in the optical parts. Second, the physics of it are just brutal. Trying to perfectly align a tiny fiber optic cable to an even tinier channel on the silicon, it's incredibly hard. And finally, you had plain old inertia. The industry was just comfortable with the old way. It was cheap, it worked, why change?
So, because of all those challenges, getting here has been a slow, step-by-step journey. We didn't just jump straight to CPO. First, we had what are called pluggable optics, which sat way out on the edge of the server. Then the industry moved them onto the main circuit board, a little closer. Then came near-package optics, even closer still. And now, finally, we're taking that final, massive leap of putting the optics right inside the same package as the chip.
Okay, so that's the billion-dollar question, right? What changed? Why is this idea that's been kicking around for 10 years, facing all this resistance, why is it suddenly the hottest ticket in the hardware world?
Well, for one, the problem just got too painful to ignore. This quote from a VP at NVIDIA really says it all. They projected that a whopping 10% of the total power of a super expensive, powerful AI GPU would be wasted just on communication. Not computing, just talking. The inefficiency just hit a tipping point.
And then generative AI exploded onto the scene. ChatGPT and everything that followed. All of a sudden, you have this insane race to build these massive billion-dollar AI factories. And that created a very powerful, very urgent economic reason to solve this power problem and solve it now. Suddenly, every single watt of power you could save wasn't just a small efficiency gain. It translated directly into millions of dollars of extra AI performance.
And just like that, the race was on. With that kind of money and performance on the line, all the biggest names in tech started scrambling to make CPO a reality, and fast.
I mean, just take a look at the players involved. You've got TSMC, the foundry that makes pretty much all the world's advanced chips. You've got NVIDIA, the undisputed king of AI hardware. Broadcom, who's been a pioneer in this space, and a whole bunch of innovators like IR Labs. The entire ecosystem is now dumping huge amounts of money and brainpower into getting CPO out the door.
And the benefits they're seeing, they're pretty incredible. We're talking 3.5 times better power efficiency, 10 times better network resilience. It's just staggering. These are not small, incremental improvements. This is a complete game changer for the giant data centers that are going to be powering, well, pretty much everything in our AI future.
Okay, so CPO is here, and it's solving this huge bottleneck. But what comes next? Does this get us any closer to the ultimate sci-fi dream of computing not just near light, but actually with light itself?
Right. So, is this it? Is the next step a fully photonic AI chip? Are we about to ditch electrons and start doing all our calculations with photons?
Well, the short answer is no. At least not anytime soon. Look, we have spent the better part of a century, 70 years, perfecting how to compute with electrons on silicon. The sheer inertia there, the money, the infrastructure, it's just immense. Plus, there are still some really fundamental technical problems to solve, like how to build a tiny, powerful, and efficient laser right onto the chip itself.
But here's the real takeaway. This is the big thing to remember. The rise of CPO proves that the AI revolution isn't just about code and algorithms. It's not just software. It's a force so massive, so demanding, that it's literally forcing us to rewire the fundamental hardware of our world. It's changing the very nature of the silicon and light that our entire digital existence is built on.